Okay, guys, we're on to section 10.4 where we're trying to find the area of regular polygons. So this would be any kind of regular pentagon, hexagon, octagon. And if you think about regular polygons, that includes equilateral triangles and also squares. So the formula is very simple, but there's a new line that we need to talk about, or a new segment we need to talk about that you may not know of. So in terms of a polygon is not a circle, right? But we've learned about circles. And so what we have here, if you look at this picture at the top, is we have a center of a polygon. And if it's a regular polygon, it could also kind of sort of be the center of the circle. So we have one line segment that connects that center to one of the vertices of our shape, okay? And that is called a radius. The reason it's called a radius is because that would be like the center of a circle. But we have a second segment that's important that doesn't go to one of the vertexes. It goes at a right angle to one of the sides. And that is a new term for us. That is called an apothem. A-P-O-T-H-E-M, apothem. The apothem and the radius are different, but they're related. So if we look at this first example here, I've kind of filled it in for you. The center of a polygon, for this particular polygon, we would just call that P. The radius of this polygon, the radius would be either PM or PN. Those are two, or you call that MP or NP. The apothem of this polygon, the apothem goes from P straight across at a right angle, and we would call that PA or AP. And so then we're left with this angle here, and the angle that we're left here is this entire green angle, and that entire green angle is the central angle of the regular polygon. So what we're doing today is we're going to be finding some angles because we're going to use those later. We're also going to learn the basic formula. One thing that's interesting is that if you look at a polygon, triangle MPN for this particular shape, this hexagon, it's actually an equilateral triangle. So if you look at this triangle, that's actually equilateral. Now that's special to a hexagon, but what we can talk about is that for every polygon, they're going to be chopped up into basically a certain number of congruent triangles, right? So if I wanted to figure out the area of this polygon, I could literally just find the area of one of these triangles, and if I found the area of one of those triangles, that would be the, I would just have to times that or multiply that by how many sides there are. So in other words, if you think of this yellow side as a side length, that would be like the base of a triangle. And if you think of the apothem, that's the apothem as the height, well, 1/2 times S times A would be the area of one triangle. Well, how many triangles do we have? Well, it depends on how many sides we have. And so we would multiply that by the number of sides. So we're going to look at that later. We're going to look at that formula later. But for now, we're just going to look at and try to solve for certain lengths and measurements and angles. So for question number 1, this is a regular hexagon, and it says if DE is 8, so they tell us DE, this length here is 8. What is the measure of these angles and what are these different sides? Well, FE would be a measure of 8 as well. That would mean that HE, because that's getting bisected, HE would be half that, or 4. And so then the question would be, well, how do we solve for GH? That's the trick. That's what we're going to be looking for. Let's get back to that in a second. If angle EGF, measure of angle EGF, remember, if this is a equilateral triangle, then from E to G to F, that would be 60 degrees. What about EGH? Well, half of that, remember these are bisectors, EGH would be 30 degrees. And HEG, this down here, would be 60 degrees. So now we've got to find GH. We have to find GH, that length. I'm going to kind of rotate this picture around, and I want you to think about what we've said. If I were to look at that blue triangle like this, and I were to say to you that, right, so this is G and that is F. Well, we've already established that, I'm sorry, this is H here. If we've already established that this is a length of 4, and that this is a 30, 60, 90 triangle, I can either use trig or I can use my shortcuts to figure out that if that's 4, this will be 4 radical 3, right? This would be 8, but that would be 4 radical 3 because of my shortcut. If you don't remember the 30, 60, 90 shortcut, you would just do trig, right? You would give this a letter. You'd call that say A, and you would say relative to 60, I know this is 4, I don't know the opposite, so you would have to set up opposite and adjacent. You would set up a tangent function to figure that out, or you could just remember the shortcut, which is a lot easier. Let's look at a square. Now let's think about what's happening with a square. If I look at a square, this is going to be a 45, 90 triangle. So it tells us KL, it tells us this length is 10. Well, if KL is 10, then what would LJ be? Well, that's a 45, 90 triangle. That's an isosceles triangle. So LJ would be 10. What would KJ be? What would this be? Well, if you remember your shortcuts, that would be 10 times the square root of 2. And we've already established that FKJ would be 90 degrees and KJF would be 45, right? This would be a 90-degree angle here, and that would be 45 degrees there. What is the perimeter of a square? Now this is where it's interesting. If I want to figure out the perimeter of this entire square, I need to know the length of all the sides. Well, if this half of that side of the square is 10, then a whole side is 20. And if I've got 4 sides that are all 20, that would be a total sum of 80. So now let's try to figure out the angles for some shapes that aren't so easy, that don't come from the 30, 60, 90 triangle or the 45, 90 triangle, some that have different angles. It is very important for me tomorrow when I want to solve all these to be able to figure out the area of this triangle. And to figure out the area of that triangle, I need to have a lot of angle information. So here's how we're going to do this, guys. Here's how we're going to do this. We're going to use the conjecture we learned earlier, where if you wanted to find the polygon sum conjecture, where if you want to find the total number of angles, you could plug the number of sides in. In a pentagon, there's 540 total degrees. There's 540 degrees total. But there's 5 angles. So that would mean that each of these angles is 108. But what's happening to that angle? Well, that angle is being bisected, right? That angle is being bisected. So that would mean then that this is 54 and that is 54. Do you guys see how these two angles together would have to equal 108? And since they're being bisected, the measure of angle 3 is 54 degrees. Well, if I have a triangle, here, how do I find the measure of angle 2? Well, triangle's always 180 degrees, so I would do 54 plus 90 plus angle 2 equals 180. And when you work that out, you get 36 degrees for angle 2. And then what would I do to get angle 1? Well, what I would do is I would just do 36 and double that to get 72 degrees. Another way to find angle 1, another way to work this out, is to recognize that there's 360 degrees all around here. And so if you did 360 and you divided that by the number of sides, which in this case is 5, well, 360 divided by 5 equals 72. So you get that number either way. So you can work your way forwards or backwards. Let's take a look at our next example here. This is an octagon. So in an octagon, I need to figure out the total number of degrees. The total number of degrees in an octagon is 180 times 8 minus 2. So that is going to be 180 times 8 minus 2 is going to be 1,080 degrees total. And I'll divide that by the 8 sides that I have, and I get 135 degrees. So that means that these together are 135. So then what is each of those angles itself? Well, each of these angles is, so angle 2 would be half that, or 67.5. Another way, I'll do it in blue, another way that you could figure these out is to say, well, all of these angles here have to add up to 360. And so if I did 360 divided by 8, that would mean that each of these angles here was 45. And so if I wanted to get angle 3, I would just do 45 divided by 2. And that right here, this little part would be 22.5, which makes sense because 67.5 and 22.5 are going to equal 90 degrees. So that'll add to the right angle to give me 180 for the total shape. Okay, guys, so we're almost done. What we want to do now is take all that knowledge of those angles, because tomorrow we're going to use those angles to help solve the problem. But let's just do some simple ones today, and let me give you a couple formulas to use to find the area of a hexagon, pentagon, octagon, or any regular polygon. We talked about finding the area of one of these triangles, and the area of one of those triangles, if I called that side length S, and I called the apothem A, the area of one of those triangles would be 1/2 its base, which is S, times its height, which is the apothem. That would give me the area of just one green triangle. But how many of those do I have? Well, I have 1, 2, 3, 4, 5, and 6. And so I have 6 total triangles, which also happens to be the number of sides I have. So a formula that I use is a little different than the formula I printed here. And the formula I use is 1/2 SAN. S stands for side length, A stands for apothem, and N stands for the number of sides. And so if you look at this here, you might say to yourself, well, Mr. Ashby, why did they use the letter P there? P just stands for the perimeter. And how do we get the perimeter? Well, the perimeter of a regular polygon is just the length of each side times the number of sides. So sometimes it's easier to use the formula on the left here, and sometimes it's easier to use this formula on the right. I'm going to use the formula on the right to solve our 2 examples. The area is going to equal 1/2 times S times A times N. So area is going to equal 1/2. It says it has a side length of 6. It says the apothem is 4. But it says it's a pentagon. So how many sides does a pentagon have? That's right, 5. So 5 times 4 is 20, times 6 is 120, and half of that would be 60. Unfortunately, I didn't give you any units here, so we would just say 60 square units. What about for our last example of the day? The area is going to equal 1/2 times the side length times the apothem times the number of sides. Well, what is the side length? 10, it tells us in the question. What's the apothem? 8.66. A lot of times you're going to get decimals with these. That's okay. And what's the number of sides? Well, it's a hexagon. So how many sides does a hexagon have? Hexagon has 6 sides. So when we multiply all that together, 6 times 10 times 1/2 times 8.66, we get a total of 259.8 units squared. Guys, do the worksheet attached, submit that to Schoology, and tomorrow we'll get into how to solve these if maybe we're not given one of these pieces of information? What do we do if they only give us the side length? What do we do if they only give us the apothem? Can we still solve it? And the answer is yes. And how we solve it is by using all that angle stuff that we spent the first half of the lesson on. All right, guys, fill out the worksheet, turn it in, and have a good day. I'll talk to you tomorrow.